When I look up at the night sky, one of the first assumptions most people make is that the stars are permanent, steady, and unchanging. But the truth is far more interesting than that. What if I told you that one of the most famous stars in our night sky didn't behave the way we expected? And for a moment, it made the entire scientific community pause and take notice? I'm talking about Betelgeuse, a star so massive, so bright, and so well known in the constellation Orion that it has been observed for thousands of years. Yet suddenly, it began to change in a way that caught even professional astronomers off guard. Because in astronomy, when something familiar starts acting unfamiliar, we don't ignore it, we investigate it. And what happened next turned Betelgeuse into one of the most talked about stars in modern science. The Great Dimming Event. Between late 2019 and early 2020, something unusual happened to Betelgeuse, a star that has been one of the brightest and most familiar points in the constellation Orion. It began to fade, and not in a small, subtle way. Over the course of just a few months, Betelgeuse lost a significant portion of its brightness, enough that even casual observers could notice Orion looking slightly off. For professional astronomers, it was immediately clear that something unusual was unfolding. Now, in astronomy, stars do vary in brightness. That is normal. Many stars pulse, shift, and change over time due to internal processes. But what made this event different was the speed and magnitude of the dimming. A star of this type does not usually change so dramatically in such a short period. That is what caused the scientific community to pay close attention. Observatories around the world began tracking Betelgeuse continuously, collecting data across multiple wavelengths, visible light, infrared, and more, trying to understand what was happening. And when a well-studied star suddenly behaves outside expected patterns, the first reaction in science is not panic or speculation. It is measurement. It is data collection. It is trying to separate what is real from what might simply be a temporary or local effect. This moment is what became known as the Great Dimming of Betelgeuse, a phase that briefly made many people wonder whether something extraordinary, even catastrophic, was about to happen in our cosmic neighborhood. Why the scientific community was alarmed. Now, the important question is not just that Betelgeuse changed, it's how it changed. In astronomy, stars like Betelgeuse are classified as red supergiants, and they are already known to be unstable in their late stages of life. So some variation in brightness is expected. But what made this situation stand out was the combination of speed and intensity. The dimming happened relatively quickly on cosmic timescales, just months, and it was significant enough to reduce the star's brightness by a large fraction. For a star that has been observed consistently for centuries, that kind of shift is not something you casually ignore. So naturally, scientists began asking what could cause this. And when you see a massive aging star behaving in an unexpected way, one of the first theoretical possibilities that comes to mind is a supernova, the explosive death of a massive star. Now, I need to be very clear here. This was not a conclusion. It was a hypothesis worth testing. Because Betelgeuse is already in a late stage of stellar evolution, where it is fusing heavier and heavier elements in its core, that makes it, in principle, a candidate for a future supernova. So when its brightness dropped suddenly, it was reasonable for some scientists to briefly consider whether this could be an early warning sign. At the same time, the scientific process does not stop at the most dramatic explanation. It pushes further. It asks what else could produce this effect. That tension between dramatic possibility and careful evidence is exactly what made the Great Dimming so scientifically exciting. What makes Betelgeuse so extreme? To understand why the behavior of Betelgeuse drew so much attention, you first have to understand what kind of star it actually is. Betelgeuse is what we call a red supergiant. That already tells you something important. It is not a normal star like our Sunday. It is a star that has entered one of the final and most dramatic stages of stellar evolution. In terms of size, it is truly enormous. If you placed Betelgeuse at the center of our solar system, its outer layers would extend far beyond the orbit of Mars and potentially reach out toward Jupiter. That means it would literally engulf the inner planets, including Earth. And yet, despite that massive size, it is surprisingly diffuse. Its material is spread out across such a huge volume that its average density is extremely low. In fact, lower than the air around us in some regions. So you are dealing with something that is physically enormous, but not solid in any familiar sense. This combination of size and structure is what makes red supergiants so fascinating. They are not stable, tightly bound objects like smaller stars. Instead, they are extended, turbulent atmospheres held together by gravity with powerful internal processes constantly moving material around. Betelgeuse is also one of the brightest and most recognizable stars in the night sky, forming the shoulder of the Orion constellation. Its reddish color comes from its relatively cooler surface temperature compared to stars like our Sun, which gives it that distinct, almost glowing ember-like appearance. So when you combine all of this, its size, its instability, its late stage of life, and its visibility from Earth, you start to understand why even small changes in Betelgeuse immediately attract serious scientific attention. Life cycle of a massive star. When we talk about stars like Betelgeuse, we are not talking about long, quiet lives like our Sunday. Massive stars live fast, burn intensely, and evolve dramatically over relatively short cosmic timescales. The reason for this comes down to physics. A star's life is a constant battle between gravity pulling inward and nuclear fusion pushing outward. In massive stars, gravity is much stronger, which means the core pressure and temperature become extremely high. As a result, they burn through their nuclear fuel much faster than smaller stars. A star like Betelgeuse begins its life fusing hydrogen into helium, just like our Sunday. But once the hydrogen runs out in the core, it doesn't stop there. It expands and begins fusing heavier elements in layers, first helium, then carbon, then oxygen, and eventually even heavier elements like neon and silicon. Each stage is shorter than the one before it. Hydrogen burning can last millions of years, but later stages, like silicon burning, may last only days or weeks. This is why massive stars become increasingly unstable toward the end of their lives. The core is constantly changing, collapsing, and readjusting under extreme pressure. Eventually, this process leads to the formation of an iron core. And this is where everything changes. Iron is unique because fusing it does not release energy, it consumes energy. Instead, so once the core becomes mostly iron, the star loses its ability to support itself against gravity. At that point, collapse becomes inevitable, setting the stage for a supernova explosion. Is Betelgeuse about to explode? Now, this is where the excitement and misunderstanding often begins. When astronomers say a star like Betelgeuse could go supernova anytime, they are not talking about days, years, or even centuries in most cases. They are talking about a broad cosmic window that could range from thousands to tens of thousands of years. That sounds vague, but in astronomy, it is actually a very constrained prediction. We know Betelgeuse is in its final evolutionary phase, and we know it will eventually explode as a supernova. The uncertainty is not if, but when. The important thing to understand is that stellar evolution does not come with a countdown clock we can read directly. Even with modern telescopes, we are interpreting complex internal processes from the outside. That makes precise timing extremely difficult. So when people hear it could explode at any moment, it creates the impression of immediacy. But scientifically, any moment still exists within a very large timescale. What makes Betelgeuse fascinating is not that it is about to explode tomorrow, but that it is close enough in cosmic terms that we are observing one of the final chapters of a massive star's life in real time. What a Betelgeuse supernova would look like. If Betelgeuse were to explode as a supernova in our lifetime, it would not be a subtle change in the sky. It would be one of the most dramatic visual events humanity has ever witnessed. First, let's be clear about distance. Betelgeuse is about 650 light years away. That is far enough that any explosion would not harm Earth, but close enough that the light show would be extraordinary. When the explosion happens, the brightness would increase extremely rapidly. Within days, the star could brighten to a level where it becomes one of the most visible objects in the night sky. In fact, it could become as bright as a full moon, casting noticeable shadows at night. This is not just a point of light anymore. It would appear as a brilliant, steady beacon in the sky, visible even during daylight hours for a period of time. Imagine stepping outside during the day and still seeing a second star shining alongside the Sunday. That is the kind of event we are talking about. The peak brightness would likely last for weeks, possibly even a few months, before it begins to gradually fade. But the event would not end quickly. Even after the initial explosion fades, the expanding supernova remnant would remain visible for years, slowly spreading into space like a glowing cloud. From Earth's perspective, it would feel like the sky itself has changed. Orion, one of the most familiar constellations, would suddenly look completely different. But despite its dramatic appearance, it would still be a safe event for life on Earth. The energy released would be immense, but at this distance, it would not be enough to damage our atmosphere or harm the planet. So what we would witness is not destruction, but transformation. A dying star turning into one of the brightest cosmic displays ever recorded by human civilization. Is there any danger to Earth? Whenever a star like Betelgeuse comes into discussion, one of the first questions people naturally ask is whether we should be worried here on Earth. It's a fair question, because the word supernova sounds dramatic, and in many ways it is. But distance is everything in astronomy. Betelgeuse is roughly 650 light years away from us. That might sound close on a cosmic map, but in reality, it places the star far outside the range where it could pose any physical danger to Earth. To put it simply, it is distant enough that even one of the most powerful explosions in the universe would arrive here as a visual and scientific event, not a destructive one. A supernova releases enormous energy in the form of light, radiation, and high-energy particles. However, those harmful components, especially gamma radiation and fast-moving stellar debris, lose their impact with distance. By the time anything from Betelgeuse reaches our region of space, it would be spread out and weakened to the point where it cannot affect Earth's atmosphere or biological systems. In astrophysics, there is a rough safety boundary for nearby supernovae, often estimated within about 50 light years or so, where serious atmospheric effects could occur. Betelgeuse is more than 10 times farther away than that threshold. That difference is enormous in cosmic terms. What would reach us, however, is something very interesting scientifically: neutrinos. These are extremely light, almost invisible particles that pass through matter with almost no interaction. Trillions of them pass through your body every second, even from the sun, without you ever noticing. If Betelgeuse went supernova, we would detect a burst of these particles hours before the light actually arrived, giving scientists a rare early warning signal. So the reality is simple. There is no danger to Earth from Betelgeuse. No threat of radiation damage, no atmospheric stripping, no planetary impact. What we would get instead is something far more valuable scientifically: a front row seat to one of the most powerful natural events in the universe, safely visible in our night sky, the real cause of the great dimming. Now, after all the speculation and excitement, the actual explanation for the great dimming of Betelgeuse turned out to be far more grounded in astrophysics than many early theories suggested. What likely happened was not a supernova precursor, but a massive stellar eruption. Betelgeuse, like other red supergiants, has a very unstable outer atmosphere. It can violently eject large amounts of material from its surface into space. In this case, the star expelled a significant cloud of gas. Once that material moved away from the star, it began to cool rapidly in the cold environment of space. As it cooled, it condensed into dust, forming a thick, uneven cloud. From our point of view on Earth, that dust cloud drifted into the line of sight between us and Betelgeuse. So instead of the star actually becoming dimmer in its internal energy output, what we were seeing was its light being partially blocked. In simple terms, it was not the star fading, it was the view of the star being temporarily obscured. This is a crucial distinction in astronomy because it reminds us that what we observe is not always a direct reflection of what is happening inside a star. Sometimes the space between us and the object plays a major role in shaping what we see. What scientists learned from this event, the Great Dimming was not just a curiosity, it became an important scientific opportunity. For the first time, astronomers were able to observe a red supergiant undergoing a large-scale surface eruption in real time. This allowed them to connect theory with direct observation in a way that had not been possible before. One of the key discoveries was that mass loss in massive stars can happen in sudden, violent bursts, rather than only through slow, steady stellar winds. This changed how scientists think about the late stages of stellar evolution. It also improved our understanding of dust formation in space. The material ejected from Betelgeuse showed how quickly stellar gas can cool and condense into dust particles, which are essential building blocks for future stars, planets, and even the chemistry that leads to life. In addition, the event highlighted how complex the outer layers of supergiant stars really are. Instead of being smooth and stable, their surfaces are turbulent, dynamic, and shaped by enormous convection cells that can span distances larger than our entire solar system. So in the end, Betelgeuse did not just surprise us, it taught us. It gave astronomers a rare, direct look at processes that were previously only understood through models and simulations. Why Betelgeuse changed astronomy? What makes the Betelgeuse event so important is not just that the star dimmed, but that it gave us something extremely rare in astronomy, direct evidence of processes we had only partially understood before. Before this event, our models of red supergiants were based heavily on theory and simulations. We knew these stars lose mass, we knew they have unstable outer layers, and we knew dust forms around them. But the exact details of how quickly and violently these processes could occur were still unclear. Betelgeuse changed that. For the first time, we observed a large-scale surface eruption in a nearby supergiant star in real time. This allowed us to refine our models of mass loss. Instead of thinking of it as a smooth and continuous process, we now understand that these stars can undergo sudden, localized outbursts that eject enormous amounts of material in relatively short periods. This also improved our understanding of stellar atmospheres. The outer layers of supergiants are not stable shells. They are chaotic, convective environments where giant cells of hot gas rise and fall, driving unpredictable surface activity. Another major impact was on cosmic dust production. The Betelgeuse event showed that dust can form rapidly and in large quantities after a single eruption. This helps explain a long-standing question in astronomy: how the universe produces enough dust to support the formation of new stars, planets, and eventually complex chemistry. So, in a broader sense, Betelgeuse did more than just behave strangely. It acted like a natural laboratory, giving us a real-time look at the final stages of a massive star's life. And every time we observe something like this, our models improve not because the universe changes, but because our understanding of it becomes more precise. Wonder of the universe. When we step back from all the data, the measurements, and the models, what remains is something very simple, a sense of wonder. The universe is not a quiet, static place. It is dynamic, constantly changing, and filled with events that unfold on scales of time and energy far beyond human experience. A star like Betelgeuse reminds us of that reality in a very direct way. What we sometimes call strange or unusual is often just a part of nature that we do not yet fully understand. And that is exactly where science becomes powerful, not when it has all the answers, but when it is still asking the right questions. Every observation, every unexpected change in the sky is an opportunity to refine our understanding, to test our ideas, and to see the universe a little more clearly than before. And perhaps the most important lesson from studying a star like Betelgeuse is this: we are not watching a fixed universe. We are watching a living system where even the most familiar points of light can surprise us. So when you look up at the night sky and see Orion, remember that nothing there is truly permanent. Everything is evolving, including our understanding of it. And that is what makes science so powerful. It turns curiosity into discovery, and discovery into a deeper appreciation of the universe we are part of.